in our 3 different ways. I'm going to skip this. Don't even put this in your notes because we did this on your packet. How do we determine whether it's a solution or not? Just plug it in and you need to get 2 trues, right? Okay. All right. So our 3 different ways to solve systems: graphing, substitution, elimination. We will be adding a 4th onto this eventually, which is matrices row operation, but we're not there yet. So, scale from 1 to 10, how comfortable do you feel with graphing lines to solve systems? 9? Does anybody feel below a 5 with graphing and seeing where they intersect?
Only when
the scale is crazy.
That's the
right.
only time I have difficulty.
Or what if the point of intersection is not a nice integer intersection number? Like what if it's decimal points and then you're estimating it? That's when it gets a little bit sketchy.
That's kind of what I meant.
Yeah. Substitution. Scale from 1 to 10. How do we feel about that? Substitution.
Let's do a few problems.
Okay, we'll do a few problems with substitution. Elimination. I feel like we need to hit that a little bit more because we didn't really do any problems yesterday of having to multiply by an actual physical number. A lot of them were just taking the negative of everything to get it to eliminate. All right, so the important thing with graphing, we're going to skip the actual graphing part, is you have 3 different types of linear systems. Okay? And these can just be rough coordinate grids, so they don't have to be that fancy. Your 3 different types of scenarios that you can have. The first type is exactly what you guys were doing yesterday. You had 2 lines, and your lines intersected. So you had something that looked like, and this does not have to be, don't worry about where the intersection point is. You're going to have 1 point of intersection, which means you have how many solutions? 1 solution. Good. We call this a consistent system. So when you have 1 point of intersection, we call that a consistent system. Okay. Well, what happens if your lines don't intersect? So we have parallel lines. Notice that didn't look very parallel. Do you have any solutions? No. So what do we say if we don't have any solutions? No solutions. What is the symbol that we use for no solutions? 0 with the cross through it, right? So if there is no intersection, we say that we have no solution. So I've got my parallel lines, never intersecting, no solution. That is considered an inconsistent system. Bless you. The third type is what happens if both of your equations technically are the same equation, meaning you only end up with 1 line. So for example, if I had x plus y equals 5 and 2x plus 2y equals 10, what happened from the first line to the second line? It just doubled, right? So if I divided out the 2 out of everything, I would get back to the original. So this is technically the same line. So I can still have 2 different equations that represent the same line. In that case, what do we say? You guys remember what we say? We don't say all real numbers. Because all real numbers would be every single thing on this graph. It's not every single thing on this graph. Well, you're kind of thinking on the right track. In the past, you guys said, what do you think, Scott?
Infinitely many
Yes, infinitely many solutions. You guys remember saying that? Well, that was back in your Algebra 2 days. So we're going to step up our game in advanced algebra because we make things more fancy, right? So every single number that falls on this line will be a solution. So, what's the equation of that line? In this case, it is let's say has a slope of 2. Y-intercept is at 1. So I'm going to say that this is at y equals 2x plus 1. It's okay if yours doesn't look like that exactly. So instead of saying infinitely many solutions, we're going to write our answer in set notation. So what does set notation look like? The set of x such that, now what I'm going to do is following suit, I'm going to write out, well I guess it's not x, it's x comma y. Ignore that because I've got both x and y. Such that, how do I write this in standard form? Move the 2x over. Can I have a negative x? Nope. So what would it technically be? So it would be negative 2x plus y equals 1. So in standard form it would be 2x minus y equals negative 1. All right, so I just want to make sure I'm doing this right. How's the book doing it? Yeah, they just write it afterwards. So what I'm going to do following this is just rewrite this in standard form. So it's the set of all coordinates, x comma y, such that they fall on the equation 2x minus y equals negative 1. Okay, because that's really specific. That's saying that I have every single ordered pair that is true for this statement. Well, every single ordered pair that is true for that statement is all the points that fall on that line. Okay? All right. That's also a consistent system because you do have actual solutions. The difference between the first consistent and the second consistent is these would be dependent of each other because it's the same thing. And the first one would be independent of each other. Okay. So all the problems that are going to be on your homework are going to be either no solution or infinitely many solutions, and how we write our answers to infinite many, the set of the values of x comma y such that are true for the following equation. So you just have to make sure you rewrite things in standard form. Okay? All right, so let's go ahead and make sure we practice all of this so that we're good to go. Can I erase this? All right. So first system. Let's make sure we got our substitution method down. 2x minus y equals 6. X equals y plus 2. Is a variable already solved for? Yes, in line 2, my x's. So what I like to do is I like to put a box around the expression that my isolated variable is equal to. And then I put a little arrow pointing to the variable that I'm going to substitute it in place of. So in place of x in the first line, we're going to substitute in y plus 2. So we got 2 times y plus 2 minus y equals 6. Distributing that 2 gets me 2y plus 4 minus y equals 6. 2y and a negative y becomes y plus 4 equals 6. So y is equal to negative 2. What do I do next? Plug it back into my y. And the reason why I like to box it is it kind of reminds me, put it back in there. Negative 2 plus 2 is?
Why is that? It's just regular.
Oh, positive 2, thanks. It would not be negative 2. 2 plus 2 would get us to 4. So 4 comma 6.
What? Why is it 4 comma 6?
I don't know. 4 comma 2.
Hey.
Ay, ay, ay.
Good.
Sorry. Like I said, I don't know how you guys function with staying up late and not getting sleep. It's been a rough 2 nights.
We're run like machines every day in here.
Because we do this every day.
You know what I mean?
I know. But with my daughter, like I wasn't getting sleep early on either.
No,
Hi. Do you need someone?
One moment, please. You don't need anything. We're just gonna step out and hold real quick.
Just a person. All right. 4-2. Good catch. Next one. 3x plus 2y equals 13. 4x minus y equals -1. Which variable would you solve for? Me personally would go for y in the second equation because I'm looking for one that has a coefficient of 1. Preferably, I want one that has a coefficient of 1 and is positive, but I don't have that. So, how do I solve that for y? Does anybody? Yeah, you could subtract the 4x and divide out the -1. But can you envision this in your brains? If I move my y over here, does it make it become positive? So then I can just move the 1 over, right? So I get 4x plus 1 when I move it over. So 4x plus 1, moving the y over makes it become a positive on the other side. So now I'm going to plug in 4x plus 1 in place of y in the first equation. So we get 3x plus 2 times 4x plus 1 equals 13. Distributing, 3x plus 8x plus 2 equals 13. Combining like terms, 11x plus 2 equals 13. 11x equals 11. X is equal to 1. So what's my y going to be if x is 1?
5.
5, good. Okay. An example or no solution? Yeah?
Quick question. Will we
Sure.
ever come across something where it's going to be, where it's going to have an exponent, or is it just going to be?
No, we're done with exponents for a little while.
Okay, because I know we didn't go over it in the previous years, but I didn't know if that was ever.
It could. Yep, we could have systems with with quadratics and cubics. Yes. We are not going to be hitting those in this chapter. Okay? All right. So far, so good. What if you had something funky like this? You can do fractions. How do we eliminate fractions? What number could you multiply that first line by to get rid of everything? 6, right? That's not that challenging.
I'm just saying we shouldn't do it.
Fractions are our friends, Nevin. 2/3 x minus 1/2 y equals 7/6. Then we got 3x minus y equals 6. So we have to multiply everything by 6 up here. I get, what, 4x minus 3y equals 7. Looks a lot nicer. Which variable are we going to solve for? Y in the second one. So move the y over, move the 6 over. So we would get 3x minus 6 equals y. Go ahead, finish it up. You'll get a fraction.
Is it -5, -21?
No. You should be getting a fraction for your x. Yeah, 11/5 for your x. The answer's up there on the board. You guys getting there? 3/5?
See what they draw.
If you ended up doing a substitution 1, I have an example in here in the PowerPoint, where it ended up getting no solution or infinitely many solutions, what would occur? Your x's or your y's would go away, and then you would be left with something like 0 is equal to 0. Can I erase this?
Get plus 18.
-3 multiplied by negative.
Yeah.
Oh, okay, gotcha.
I went to the same thing.
Got it? So if you ended up with something, I'm just going to make something up so that it worked, where you had 3x minus 3x plus 2 is equal to 2. What happens to your x terms? They go away and you're left with 2 is equal to 2. Is that true or false? That is true. So that would be one of those infinitely many solution problems. If it didn't work out and it was, bless you, equal to, let's say, 4, and you're left with 2 equals 4, then it would be
Not true.
not true.
Not true.
All right, so we're good with substitution, hopefully. I don't know what is that thing? Now let's do elimination. Let's do a trickier elimination.
Elimination?
Yeah. So 5x minus 2y equals 4. 2x plus 3y equals 13. Now the problems that you guys were doing yesterday, the variables were easily canceling out. In this case, it's not easily canceling out. So I can't just subtract and have an x or a y go away. Maddie?
Are there instances where we'll be able to get around using elimination, or are there certain equations that you can only use elimination for it?
Nope, I mean you can use substitution for any method if you don't like elimination. So what I would think about is my coefficients in front of my x are 5 and 2. My coefficients in front of my y is -2 and +3. So my first thought process is, does anything eliminate right away? No. Then I'm going to go to, well, do any of them have opposite in signs? Yes, my y's. What could I convert 2 and 3 both into? 6. So what am I going to have to multiply 2 by? 3, and 3 is going to be multiplied by 2. So now I'm going to just change my equations by multiplying them by 3 and 2. So this new line is going to be 15x minus 6y equals 12. This new equation is going to be 4x plus 6y equals 26. Now I can go ahead and just add up and down because my y's are going to eliminate. So my x term is going to become 19x equals 38. So x is equal to 2. Now you got options. You can put this 2 into either of these equations or either of these equations. I would go back to the original because they're smaller numbers. Pick which one you like, first or the second one. Top one. So if we go 5 times 2 minus 2y equals 4, then we get 10 minus 2y equals 4. Subtract 10 from both sides, 2y equals -6. Dividing gets us y equals 3. So 2 comma 3. Okay? So if your variables do not have the same coefficient, you're going to have to do some type of multiplying to make them end up having the same type of coefficient. All right. This should not be new stuff for you. Is this kind of all coming back from the back of your brain to the front of your brain? Hopefully. Okay. I'll leave that there for 2 more seconds. Are we good? All right. So now let's do a special system. 2x minus y equals 3. 6x minus 3y equals 9. Does anything eliminate right away?
Nope.
Nope. What do you want to eliminate?
I'm trying to eliminate, I'm gonna eliminate some x's.
Okay, so let's get rid of the x's. So I see a 2, I see a 6. So I can easily convert a 2 to a 6 by multiplying by, well, yeah, I want to do a negative 3, right? Because if I do a positive 3, that would make it be a positive 6 and a positive 6, which won't eliminate. So if I multiply line 1 by a negative 3, I get negative 6x plus 3y equals negative 9. This equation stays the same. 6x minus 3y equals 9. So now it happens. I get 0 equals 0. Is that true or false? That's a true. So that means it's infinitely many solutions. So we are going to write the set of the ordered pairs x comma y such that, now out of these two, which one is the most simplified standard form? The first or the second? The first, right? So then I'm going to follow that with 2x minus y equals 3. So that means every coordinate point on this line is a solution. If this would have been instead of 9, 19, then we would have gotten 0 equals 10. Is that true or false? That is false. Then we would just put a big no solution sign there. Okay? All right. So this is probably the trickiest part, is just writing the notation for infinitely many solutions. You need to write it in standard form following suit. Think you guys got it? Okay. That is all I've got for you then.